All right, so let's take a look at this problem. A couple things should pop up in your head right away. Something looks a little different. You'll notice that on this problem, the beam over the first 12 feet has an eye of twice that from C to D. So this is a beam that's deeper probably, has a higher moment of inertia, and then over the last little bit gets a little bit smaller. So this beam in some sense is tapered. Now I do have an actual value for I and a value for E. We could actually get a value for computation. It's a cantilever beam. You can see it's fixed connected here at A. So we're going to try this with virtual work and see how it goes. So the first thing I have to do is write my real expressions, or my expressions for moment in this structure. Can I write a single moment equation that's good for the whole structure? It looks like it. Part of it you could. If it were just a distributed load, you could write one equation for that. But this pesky little concentrated load here kind of messes it up. So you're going to have one expression from 0 to 6, and then a different moment expression from 6 to 20. So we'll have to write two. However you want to cut this is up to you. I'm going to do something a little different because it's a cantilever beam. I'm not going to take time to actually find the reactions. I'm going to cut the structure somewhere here, and I'm going to go to the right. That way I don't need the reactions. And when I come out here, I'm going to cut the structure and also go to the right. So it'll save me a little time that I don't have to first find my reactions at A. So when I cut the structure here, I'll just be looking at the right-hand side to find my internal moment. And same thing here. Okay? So let's do that. Since I don't need reactions, I'll just plow ahead. So this will be the real moments for this load. And I'll be looking for the first one, which will be valid from 0 to 6. That's anywhere in this range. So I'm going to cut it and look at the right-hand side. So I'm going to come up at some distance x. And then, of course, internally, I'm going to have my real moment. Now, what do I have on that beam at this part? Well, I've still got a distributed load. Oops. That didn't draw, did it? And then I'm also going to have this point load. And this is 1.2 kips per foot.
Dr. Camp?
Yeah.
Why are you able to ignore the reactions on this one, but not the problem before this?
The problem before had a pin connection here. So I did have a reaction on the right-hand side. This is a cantilever, right? So if I cut it here and look to the right, there are no reactions. Now there's internal forces, and that's what we're getting ready to find. So what is this distance going to be here? Now this is where I'm having to pay for not finding my reactions with a little more complication here. So the total distance is 20, so this would be 20 minus x. And then what's this little distance right here? Well, the distance from here to the load is 6, so it'll be 6 minus x. Everybody see that? So when I sum moments internally at this cut surface set it equal to 0, well, I've got my internal moment, which actually turns out to be negative. And I need a concentrated equivalent here, don't I? So what would be the concentrated equivalent force of this area? Well, it's a rectangle base, which is 20 minus x times height. So this force is going to be 1.2 times 20 minus x. And what's the distance from the cut to the center? it'll be the length divided by 2, which is 20 minus x over 2. So what am I going to get? This force is going to create negative moment. The force is 1.2, 20 minus x. And the moment arm is 20 minus x over 2. That's the moment about the cut of the concentrated force. And then I've got my applied force, which is 6 minus 6. And its distance is 6 minus x. So when I solve for my moment, just throw the moment to the other side. I can tidy this up just a little bit. I'm not going to go into too much detail, but that 1/2 will knock that down to 0.6, and then I'll have 20 minus x squared, and then I'll have this bit over here, which looks like plus 6x minus 36. Still not very friendly looking, but not bad. Did I get that right? Okay. So now what do you do? We've got to redo it. This time we're going to go from 6 to 20. So it's just this piece, but just a little smaller chunk to the right. Still, it's going to come up here. This will be x. The segment to the right will still be 20 minus x. We'll still have the load applied, which is 1.2 kips per foot. And then we'll have the internal moment. What I don't have anymore is I've moved past this 6 kip force. I'm to the right of that, so I don't have to worry about that. Interestingly enough, my distributed, or my concentrated equivalent force of this distributed segment looks the same. It's still a rectangle, base times height, so that's 1.2 times 20 minus x, which is the same as the previous one, but the limits are different now, right? So when I sum moments about the cut and put that in equilibrium, what do I get? Well, my internal moment is negative. The moment due to the applied force, or the concentrated equivalent force of the distributed load, is also negative. The force is 1.2 20 minus x, and the distance is half the distance, which is 20 minus x over 2. So when I solve for the moment, I get minus 0.6 times 20 minus x squared. Now I can finally check something. I do know the moment at D. What's the moment at D? It's free in. Should be 0. So I look at my equation that's valid in that range, and I put in x equals 20. What do I get? 0. So that works. I could also make sure that these two expressions give me the same moment where they share, which would be x equals 6. Okay? So now what do I do? I got to do the virtual system. What is the virtual system? Well, I want to know the displacement at D. Where is D? Out here at the free end. So my virtual moments will be from a structure that looks like this. It's still 20 feet long. But where do I want the displacement? At D, that's the end, so I put my load there, and I assume it acts down. How many virtual equations do I need to write for this? Can I write a single equation for the moment across the whole length?
Yes.
I can. And again, I don't have to find the reactions. I can cut it here, look to the right, so this would be my x value, and I can write one equation for this structure, and I'll do this. So this equation will be good from 0 to 20, and when I cut the structure, looking at the right-hand side, again, from left to right, that would be distance of x. My right-hand segment would be the total length 20 minus x. And then on the very end, I've got my unit load. Now, interior, I have the moment, but it's the virtual moment. So I'm trying to use the lowercase for that. So if I sum the moments at this cut equal to 0, what do I have? Well, I'm using right-hand rule, so my internal moment is negative. And about the cut surface, the unit load also creates negative moment. That would be negative. The force is 1. The distance is 20 minus x. So it looks like my virtual moment is simply, I'll just do it this way, minus 20 minus x. And the reason I didn't run the minus sign through is you'll notice that my other problems have 20 minus x, and it'll be just easier to lump those together. And we're done. So now what do I have to do? I have to match real moments to virtual moments at various pieces. So I know I have one match from 0 to 6 because this real expression is only good from 0 to 6. So I can match that to here from 0 to 6. And then from 6 to 20, I can match this real moment to here, except for one other thing. What happens at x equal 12? The moment of inertia changes. So I have to break that up into another integral. So I'm going to end up with an integral from 0 to 6, real moment, virtual moment. An integral from 6 to 12, real moment, virtual moment. And then another one from 12 to 20, the same ones, but I'm only dividing by I, whereas in the first ones I'm dividing by 2I. So I have a different denominator. So this is what my virtual work expression would look like for this problem. So the displacement at D is going to be the integral from 0 to 6 of, let me write it in symbolic form too. So I'm going to call this M1, M2. So really the moment in the first section, the moment in the second section, and this is for the whole length. So what I'll have is from 0 to 6, I'll have MI virtual I divided by 2EI. Why 2? Because it's twice as big. And then from 6 to 12, I'll have the second real moment expression times the virtual moment, again divided by 2EI. Again, 2 because there's 2 of that. And then the third segment from 12 to 20, the integrand, this part of the integrand looks the same. It's still the moment from the second equation and the virtual moment, except I'm dividing by EI. I left my dx's off of all of these, sorry. Newton and Leibniz would be very upset with me. I forgot the critical factor, the infinitesimal space. So see, you just have to do that. See how easy it is? Now, of course, the execution of this is going to get really messy. When you look at this thing times this thing, expanded out and integrated, I know you can do it given a lot of time, but this is not a course on polynomial expansion and integration. So this is good enough for me. If you even want to write it in this symbolic form, that's good enough for me. Now, what am I going to do? I'm going to go back to my office, again, turn on some nice music, get a nice cup of coffee, and I'm going to plug through all this crazy junk and give you an answer on a separate sheet of paper. But it won't be on the video, but I'll post it online. So that's another reason I wanted to show it to you in this format, is that this, to me, is what's important. Developing the right moment equations and then assembling them in the right way to account for all of our space, 0 to 6, 6 to 12, 12 to 20, and then all the possible things that can change. Maybe the beam tapers, different expressions for moments. That's good enough for me. So any other questions about that? And that's about a 15-minute problem, too, with all the talking and everything else. So it seems like a reasonable thing to do for exam 2. All right.